tired at the end of the day, so I'll say the most important at the beginning. What I'm going to present is mostly pictures from experimentalists. So no wave function, just rotated this. So all the list of people that did this work are experimentalists from 2 different labs in France and at the Technion. Okay, the program of today is the following: is to study a fractal spectrum and quasicrystals. So the working horse that we use is the Fibonacci chain. And then I will show you 3 different ways to define, measure what is called Chern numbers. So first we'll be using what is called the gap labeling theorem. Second, showing that Chern numbers can be written as winding numbers from the scattering theory. And third, Chern numbers from just the structure of quasicrystal, from a diffraction pattern. And then I will define the Chernometer. This is because of MIT, so we define a stiffness meter, so I felt that I have to define another meter, so Chernometer. Okay, so this is very important, but before you fall asleep, because it's late and you are tired, let me say the most important. The most important is this picture. So from this picture, you could get the idea that I'm running for many years with us, but this is an inaccurate description. In fact, I'm running for many years after us. And I'm trying to catch him each time, but not very successfully so far. So therefore, Asa, I wish you many more years of running, but just with the hope of that once I will be able to catch you. So this was in Mitzvah, the South. It was a moon run a few years ago with Yom. Okay, so this was the most important. Now our pictures. What is a fractal spectrum? Fractal spectrum, so what is a fractal first? Fractal, so this is a canonical fractal, it's called the Sierpinski gasket. And fractal is a structure that is self-similar. Self-similar means that if you enlarge it cleverly, you get the same. And this is what is called a discrete scale symmetry, as opposed to continuous scale symmetry. And this is a real fractal, but the fractal spectrum, an example of it, is given by a quasi-periodic stack of dielectric layers of 2 types, A and B, with different indices. And if you build a cavity like this, which is using this Fibonacci sequence, where you concatenate the 2 previous sequences, then this cavity has a spectrum that you can study numerically. Not yet. Yeah, already.
No, I just wanted to interject a very brief joke, which is relevant to this, which is a riddle, which is what does the V stand for in Benoit v. Mendelwald? And the answer is Benoit v. Mendelwald.
Okay, so I had another joke about this, but I will skip it for afterwards. So anyway, so the spectrum of this guy, I mean the eigenmodes of such a cavity, it looks like this. So this is density of modes. And indeed, if you enlarge it cleverly, it reproduces the same, and again the same. So this has apparently discrete scale symmetry. And a way to describe more formally this symmetry is by defining the counting function, which is the number of modes that exist in a given window, delta omega, around a given frequency. And if you enlarge it by a given factor which is fixed, b, then you get the density of the integrated of the counting function here, which is related to the previous one, with another fixed number that is called a. Okay, that has a given time. And if you do it again, you get the same kind of relation with a squared and b squared, and you can do it p times, and you get this expression. So this is expression of the discrete scale symmetry. Very good. So then we get an equation of that sort. It's called a scaling equation, where a and b are just fixed, and they depend on the fact that you have a Fibonacci sequence. For another system, it will be different, but they are fixed. Okay? They are not whatever you want. And the general solution of this equation is of that form. It is a power law, delta omega to the power alpha, where alpha depends on those two parameters A and B, like this, times the function, which is a periodic function of period 1, of the log of delta omega divided by the log of the same b that we did. So this is the general solution of this scaling equation. Very good, and you see that if you try to implement it numerically, it works quite well. You see that this expression for the Fibonacci has those two features. One is power law with this exponent that we found numerically, which is we can calculate it also analytically, and you see that there are those log periodic oscillations. So this function is difficult to calculate, usually it depends on the structure, but you see that it exists. Okay, so this is the fractal structure of this spectrum.
This 0.78 is decided by what?
A and B. It's fixed by A and B, and A and B depends on an A and an B, but you can calculate it analytically. Analytically, it's 0.77, etc. It has been calculated a long time. I mean, there is nothing, almost nothing new to calculate. Okay, by the way, no, this is so now how to see this fractal energy spectrum experimentally. So experimentally, what the group in France has been doing is to use cavity polaritons. So polaritons are objects. It's a quasi-particle that's arising from the strong coupling between a photon and an exciton, and that lives in a cavity mode, which is here between Bragg peaks, between Bragg reflectors, Bragg mirrors, and they are just two-dimensional here. Okay? And what they did, instead of building this kind of cavity that I discussed a second ago, they just sculpted this polariton cavity with this potential, which is precisely this Fibonacci potential. Okay? So the polaritons, they live here in a section of those wires. There are 3 of them here, and they consider 233 letters long cavities. Okay? And the polariton, they live here in this section. Very good. From this, you can build an effective one-dimensional model, and which, so the polaritons, they obey this Schrödinger equation, and this potential has 2 components. One component that describes the structure of each letter here, and one component that describes the fact that we have Fibonacci series. Okay, so this is this potential. And now those are the measurements. So the measurements, they measure the spectral function, which is the energy as a function of k in such a structure. So how do they measure this? In fact, they excite those polaritons with external light. And the beautiful fact about polaritons is that you can measure the light that is emitted in a given direction, that is given by this angle theta, and this is directly related to the k in plane of the polaritons. So by measuring the energy for this angle, you get E as a function of k, and it looks like this. Okay? So this is an experimental picture. This is a trace of this spectrum. And this is a more quantitative description, just to show you that with our numerics, with our own theoretical model, we know how to reproduce the spectrum. So this is the experiment. Okay, this is E as a function of k, and this is the theoretical calculation, so you see that it works there. Okay? But now you see that we have many gaps in this spectrum, and the idea is to label the gaps. And to label the gaps, in fact, they did a second experiment. And the second experiment is now not to measure the energy as function of k by just looking at a given direction and measuring the energy of the photons that are emitted here, but now to integrate over all possible k's and to measure the total intensity. So this is the total intensity integrated over all k as a function of the energy of the incident photon. So you get something like this. And if you integrate this, you get what is called this integrated density of states, which is the counting function that I defined before. Okay? Now, this counting function, again, if you compare the experiment and the theory, you see that it works very well. And this counting function has gaps here. Okay, so this is between 0 and 1. There is no, no units or whatever. Everything here has units. It's not whatever units. And this function, this integrated density of states, is nothing but the envelope of this function. And if you're not completely convinced about this, if you just rotate this integrated density of states and compare it with this, you see that where there are gaps is precisely the plateaus of this function. Okay? So the idea is that you can label each of those plateaus with 2 integers. And this works extremely precisely. Neat. So far so good. Follow? Very good. So now the beautiful result is for the Fibonacci chain is that you can label those gaps, those plateaus, with 2 integers, p and q, according to this expression, which is extremely simple. Okay, tau is the golden mean, and the integrated density of state, the value of this here, is just given by this. Okay? And it works very well. Now, those 2 numbers are called the Chern numbers. Okay? And they are topological invariants, they are independent of the potential strengths, etc. And this is our first encounter with those Chern numbers. They label the gaps of this fractal spectrum. And this spectrum is indeed fractal because if you look at this integrated density of states and you try to get it experimentally, so this is the blue trace here, you see that indeed it has a power law times log periodic oscillations. So here you see 1 oscillation, 2 oscillations, and almost 3 oscillations, which means 3 orders of magnitude for the energy. You see? So this is the proof that this spectrum is a fractal spectrum. Okay? It's not enough to have a power law. You need those log periodic oscillations. Okay, so we have a fractal spectrum, and we have Chern numbers to label the gaps of this spectrum. So now, a second way to define Chern numbers is to describe them as winding numbers. So what's the idea? First of all, how to build the quasi-periodic chain. There is one way to do it, which is the following. You define this function. This is a very simple function. This function is the sine of difference of 2 cosines. So this is just a number, okay? Cosine of pi divided by tau. Tau is the golden mean. And this is cosine of 2 pi n divided by tau plus some phase, okay? And you call it chi n. So when this guy is equal to -1, you call it b. And when it is +1, you call it an a. And now you build a sequence like this, chi 1, chi 2, chi n, up to a given value n that, of your choice, okay? And if you translate it into A and B, what you obtain here is a Fibonacci chain. So it's a way to build a Fibonacci chain. Okay? And
for what value of time?
So whatever value of phi. Whatever. So this is the point. Now this and
You also take negative values of little animals?
no, I just I defined it.
You have an edge to this.
Yes, I have an edge. So this phi is just a variable that I can put here, and it's a legitimate degree of freedom. It's a very important one, although usually it is ignored. And when it is not ignored, it is considered a nuisance, but here it is not. Here it's very important. Cool. So let's see what it means, phi. In fact, when you change phi, you see that you will change this sign here, and if I consider now the infinite Fibonacci chain, so this is a chain, the infinite one, okay? For each value of phi, in fact, by changing phi, I will move along this chain. You're with me? So, here is an example. I take, this is the infinite chain, the same chain, and I take now n is equal to 89 as an example, and phi, I put phi equal to 0. Just I put it. And I go along this chain, and I see that the sequence that I generate is this one. Okay? So this is the one sequence of the Fibonacci chain, and I put it here. Okay? So this is the same chain here. And now I change phi, I look at phi equal to 0.1. And I'm going along the same chain, looking where is this chain that I generated. And it is here. Okay? So you see that by changing phi, in fact, I do a translation along the infinite Fibonacci chain. And now this new chain, I put it on top of the previous one. And you see that they are almost the same, they differ by just one change here. Okay? So this is the only important thing to remember. I told you there are only pictures. You with me? And now, okay, now let me just do it 3 times and then you will tell me if you understand. Now I do it for another value of phi. I put phi in this definition, which is equal to this value. I generate a chain. Okay? And this chain, I go along the infinite chain to see where it is. Oh, I found it here. Here it is. And this chain, now I put it on top of the 2 previous ones. And this is what I obtain. And you see that it differs from the previous one by just small changes. It's almost the same, but not exactly the same. Okay? And I can do it because phi is a periodic variable. I can do it the number of times, and then I generate this whole picture. So this whole picture, for each on the x-axis here, you have a given chain. And here you change just phi. And since it is periodic, you change it between minus pi and plus pi, and you get everything. You get all the possible realizations of 89 Fibonacci sequences. There are not more. All of them are here. And of course, in the infinite chain, they repeat themselves an infinite number of times. But this, you have everybody here. Okay, so this is the picture, and you see that in fact, for each value of phi, you can have either 0 changes or 1 change. Okay, so here is just one value of phi. You can see that here you can hit the change or not. So you get this picture. And here are all the possible changes that you can generate. And you see that in fact, they generate a pattern that looks very old. It's a pattern of changes. Now the question is there a symmetry of the Fibonacci chain that is probed when you scan the phase phi. Okay. And the symmetry that you observe is what is called a palindromic symmetry. And the palindromic symmetry is in fact when this sequence that you read that way is equal to the sequence that you read the opposite way. It's a mirror symmetry. Okay? And what you see is that when you scan phi, in fact, this is a parameter that is defined here that defines the deviation from palindromicity. When this parameter is 0, the chain is palindromic, the way I defined before. When it is different from 0, it is not palindromic. And you see that in a given cycle, the chain is always palindromic twice. There are 2 values of phi for which the chain has this mirror symmetry. Only 2. It cannot be more than this, and this is independent of the length of the chain. It will be always 2. Okay? Very good. And now, all this is structural properties. Are there spectral consequences of this structural property? And so, you remember what we saw. So all those are chains for different values of phi. And what I claim is that each sequence has exactly the same energy spectrum as the one I had shown you before. Which means that the spectrum does not depend on the value of phi. Okay? They are all the same, all of them. Which means that what we saw before, this integrated density of states with this nice gap labeling and all this is independent of the phi, of the phase phi, independent. Okay? In order to see this, there is a very nice formalism, which is called the scattering formalism. And this formalism tells you that if you look at your system as a black box, this is our Fibonacci chain, and you probe it with scattering waves, then you can describe it by a 2 by 2 unitary scattering matrix. And this matrix, in fact, can be described using 2 phases, phi 1 and phi 2. And one phase is called the total phase shift, which is the sum of the 2 phases. And there is another one, 2 independent phases, right? And there is a very nice result, which tells you that if you look at the density of states of such a system, this density of states is related to the total phase shift through this very nice relation. So this relation, each time that I give it a name, I say Schwinger relation, first time. So somebody is sending me a mail the next day saying, no, 10 years before there were another one. So this is a relation, this is as old as the Kepler rules. Okay? So like this, I'm on the safe side. So this is a very known relation, which gives this density of states in terms of just the total phase shift. Now, if you apply it for the Fibonacci chain, this one, this is the density of states that we obtained. That's what I showed before. And indeed, you see that if you scan, you change phi, the spectrum is absolutely independent of phi. The spectrum remains absolutely the same, which means that the total phase shift is independent of the modulation phase delta phi. Independent. So, different structure, but the same spectrum. But if now you compare, so you remember that for a 2 by 2 matrix, unitary matrix, there are two different phases, two independent phases. One is the total phase shift, which does not depend on phi, but there is another one. And the other one, you probe it while comparing the same Fibonacci sequence, but with an incident wave on that side and an incident wave on that side. And you see that in fact, the second phase, which is the difference between those phases, angles here, which I call alpha, this will depend, in fact, on delta phi. Because if the structure is palindromic, then this phase will be 0. But if the structure is not palindromic, the phase will not be 0. And indeed, this is the palindromic cycle that we saw before. And if now you look at this phase as a function of phi, you see that indeed it follows this palindromic cycle. Which means that this second phase is dependent on the palindromic symmetry. But this does not determine the spectrum of the chain, only the chiral. So how to observe this chiral phase? You cannot do it on a scattering state because they are independent of the phase, so you do it on edge states. But then you have to generate edge states. How do you generate edge states? You take your Fibonacci chain and you put a mirror. Okay? But this is not really very good to use scattering formalism, so then I just unfold this chain, and so this is equivalent to this, and this I can just describe using an S matrix, a scattering matrix. Okay? But this chain is not a Fibonacci chain, okay? So therefore the spectrum of this will not be that, but it will have additional modes, which are gap modes, which are because of this additional mode E. And those are the gap modes. So you see there are additional modes. The spectrum, the gap locations remain unchanged with respect to the original structure, but here you have additional modes. And you see that those modes, the location of those modes in the gaps depend on delta phi. So if you change delta phi, you have modes at different places. Okay? And now what is nice is to see how those modes, they cross over the gaps when you change phi, when you change the value of phi along this palindromic cycle. And this is the way, how they change. So this is the spectrum, you see the gaps, and here are just the way that those edge states move through the gaps as a function of phi over a period. And you see that they do it differently. And how they do it? First of all, first thing is that when you have a palindrome, which for those two values of phi, where you have a palindrome, there are no edge states. Okay? The edge states, they disappear completely at the moment that you have a palindrome. Why? Because then the structure is an exact Fibonacci. So then there is no reason to have edge states. But when the chain is not palindromic, then you see that you have those chains, those edge states. And now look how they move through the gaps. So you remember that for each gap, we have those Chern numbers. So those Chern numbers here for this gap, this is Q equal 1, Q equal to 6, to minus 2, etc. And look, this is the way that the modes goes through the gaps. For Q equal to 1, for instance, it goes with a period 2. And for Q equal to minus 1, it goes with the same period, but with the opposite sign. Q equals 2, it goes with period twice as large. And minus 2 with twice the same period, but with the opposite sign. So you see that, in fact, the way that the edge states move through the gaps is directly related to the Chern numbers. Okay? And in fact, so the Chern numbers describe the way that the edge states move through the gap when you change this structural phase angle delta phi. Now, what you can show is that this chiral angle that I defined before the winding number of this phase is just the Chern number. Okay? So this is in fact up to a factor of 2, and this factor of 2 is because of palindromism. So it's another way just to define those Chern numbers. They are the winding numbers of this chiral phase. Okay, so this is the little bit of theory that I wanted to show you. All the rest are just experimental pictures. So this has been observed experimentally recently using the same polaritons. So you remember those polaritons, the spectrum. But now what they did was just to build this Fibonacci, anti-Fibonacci, to have an interface and H states, and for different values of phi. So each value of phi is a different realization. So here what they did was 89 different samples. So 89 different values of phi. Okay? And this is the experimental picture. Okay, so this is the spectrum. So you see that in the gaps there are additional H states. So you see it for Q equals, in the gap Q equals to plus 2, in the gap Q equals to plus 1, to minus 1. And you see here the real space imaging. So this is the wave function, squared. So this is a measurement of the wave function in the gaps. You see those H states here in the gaps? So this is one H state, this is another H state, etc. Okay, so this is in the energy spectrum, this is in the real space. And now this is the picture that I showed before. This is what we expect, and this is the experimental result. You see that indeed, when you change phi, there are H states that move through the gaps, and they move through the gaps exactly according to the corresponding Chern number. So this is Q equal to minus 1, so give it a sure. So this is Q equal to minus 1, it goes that way. Q equal to plus 2, you see it as a double period and an opposite sign. So like this, and measuring the winding number of this, you get precisely this Chern. So it's an experimental way to measure those Chern numbers. Okay, so there is another way to look at this. It's to look at the wave function in real space. And you can measure also the Chern number from this wave function. So this is the measure square of the wave function. And you see that when you change phi, look, for a given value of phi between 0 and a quarter of a period, the Q equal to minus 1 mode has a minimum here, and the plus 2 has a maximum. And when you change phi, you see that a minimum remains a minimum in the second quarter of a period, but here you change sign. And you change phi according to the Q. And this is what you obtain. So this is the trace of this maximum. So you get plus for Q equal to minus 1, you get the maximum and the minimum. Minimum here, maximum here. And this is just the measurement of the Chern number on the wave function. The wave function, not on the energy. So then you could get the idea that topological Chern numbers in quasicrystals are of spectral origin. But this is not really the case. In fact, you can measure those Chern numbers just without saying the word Hamiltonian of spectrum. So how you do this? You take your Fibonacci finite string, this one. So this is another experiment that has been done at the Collège de France with those people. So you take this chain, and in fact you have a realization of this chain using DMD. DMD are just mirrors like in this beamer, okay? And this is a DMD, this is a set of mirrors which are such that when it is an A, it reflects light, and when it is a B, it does not reflect light, okay? And like this you can build this Fibonacci chain. And now what you do, you just shine on it a laser, and you look at the diffraction pattern of this picture. So this has nothing to do with spectrum, just diffraction pattern of this. And this is the trace that you obtain. So this is the diffraction pattern of a given realization. Okay? So how is it related to the transmission spectrum that we showed before? And there is a relation. You see that this is a transmission spectrum that we saw before. And each time that you have a gap in this spectrum, you see that in the diffraction pattern there is a peak. Okay? So there is a relation between the two. And now the question is, how can you measure those Chern numbers using this? 2 minutes. Very good. So one possibility is to take a Fibonacci, and you make a juxtaposition of two identical Fibonacci chains. So this is one Fibonacci, one Fibonacci. And now you measure the diffraction pattern of this guy. And this is what you obtain. When you change, you see where there are the gaps. There is, you see an interference here, diffraction peak, but it does not depend on phi. Okay? There is no effect on phi, and therefore you cannot measure Chern numbers from this. But now do the following. Instead of considering this Fibonacci, you consider Fibonacci and an anti-Fibonacci, what we did before. Okay? And this is the new pattern that you obtain. So you see that this now it's different from this. You see there is an interference pattern here. So this is in fact a Young slit experiment. Okay? And now, if you look at the given value of kx here, what you see as a function of phi is this beautiful oscillation, and the period of this oscillation is precisely the Chern number that corresponds to this gap. So this is a Young slit experiment or out of Bohm experiment with quasicrystals. And here there is no spectrum, there is no spectrum, just do a diffraction. But you can do better. So this is this oscillation, and this is the last, this is the Chern number. So how you can do better? So now, instead of considering this, the diffraction of this single realization, I look at all the realizations that I presented before. The 89, so this was 89 realization. Okay, I take this. And now what I do is this diffraction pattern here. I do a diffraction pattern of the total. And what do you observe? So you observe this. You see, you observe a structure where here in the x-axis you get points at the values of the gap. And on the y-axis here you get only integer numbers. And those integer numbers are precisely the Chern numbers that are describing the peaks. But here you see Chern numbers up to, so this is the whole picture. If you have a chain of size n, in fact you see n values of the Chern numbers. Here you see 89 Chern numbers. So this is an experiment where you can measure Chern numbers up to 89. Where for spectral measurements you can see 2, 3, 4, 5. Here you see all of them in one short experiment. So this is the measurement. Okay? So for each point, the value here gives the Bragg peak, the gap, and the value here gives an integer. It's exactly an integer, which is a Chern. So this is a Chern. Okay? One short experiment. So the idea is that you can build beautiful pictures out of this, torus, quasi-brilliant zone, and beautiful things, but this is the end. So let me just summarize all what I said. We demonstrated the fractal structure of the energy spectrum of a Fibonacci cavity using polaritons. We saw that topological features in quasi-periodic chains can be displayed using this palindromic symmetry. We can measure gap Chern numbers as winding numbers of the chiral phase. The gap traversing of edge states is completely determined by the corresponding Chern numbers. And you can do it just using scattering theory. And you can also determine Chern numbers from just the structural data of the Fibonacci chain. And the idea is that you should never underestimate information contained in 2 by 2 matrices. So, thank you for your attention. And again, Asa, many more moon runs and M2Vs together also. So thank you.
I'm trying to relate what you said to, much simpler things that I know. So
No, there cannot be something simpler than this. No, there is nothing simpler. So something more complicated that you know.
So suppose I have a ring and with no breaking of time reversal symmetry. So if I measure the and suppose my potential is palindromic. So going clockwise, going anti-clockwise, I will accumulate the same orbital phase. Now, if I want to have the phase, I think you call it alpha, which is the periodic phase, I just introduce some all of Bohm phase. So going clockwise or going anti-clockwise will give me different phases. So is what you're talking about essentially the introduction of Aharonov phase into this structure.
It is much simpler than this, I told you. There is nothing very much simpler than this. This phi is in fact a kind of Aharonov flux, and this young slit experiment that I showed, you can call it Aharonov effect if you want. This is precisely what it is. Indeed. But here, okay, here the phi is just this structural angle that you put into the way that you build the quasicrystal.
Could you go back to your expression that you had 10 slides back for the Chern number of integrals?
The winding number?
Yeah. Yeah. There. Right. So, so I don't understand everything here, but so clearly you have integers here. There are probably topological integers. I'm trying to understand the connection with the Chern numbers as the integral of some curvature over some even dimensional manifold, presumably two-dimensional here. So what is there some curvature or some
Yeah, maybe. Well, if you ask me, can you write it as just the integral of a very curvature?
Yeah.
Well, I don't know. But what I know, I don't know. So this is the answer. Not fair. But what I know is that if you want to understand this, you can in fact look at this picture, this nice torus that I showed at the end. This one. And in fact, the Chern numbers, there are all possible ways to do winding around this torus. So this torus is the picture that we did this before the diffraction. And this is exactly a torus. So this guy that was before is exactly a torus. Okay, you can close it. And the way to wind around this torus gives the different Chern numbers. So it is indeed this. So now, okay, if you want to write it as the integral of a very curvature, I guess it's possible, but I don't know to do this. But this is the torus in the real space, but you can do it also in reciprocal space. This is the same torus, but in reciprocal space.
Okay, so let's thank Eric and all the speakers.